Yeah. In the last lecture, we were looking at the salient characteristics of the flow in a pipe. Okay. One of the central ideas here is the transition between a laminar and a turbulent flow. Okay. And the Reynolds number based upon the average velocity and the pipe diameter is less than about 2100. The flow in the pipe is laminar. In a cylindrical pipe, the velocity profile is parabolic and the streamlines are straight and smooth, and there is no fluid velocity fluctuations perpendicular to the streamlines, and transport across streamlines takes place by molecular diffusion. At a Reynolds number of about 2100, there is a spontaneous transition to what is called a turbulent flow. And in a turbulent flow, the velocity profile is flatter at the center and the velocity increases steeper at the wall in comparison to a laminar flow. The streamlines are no longer smooth and steady. There are large velocity fluctuations perpendicular to the flow, perpendicular to the average flow. These velocity fluctuations are due to the motion of correlated motion of parcels of fluid called eddies, and these eddies transport mass, momentum and energy across the flow. The transport by eddies is much more efficient than the transport by molecular diffusion, because of which the transport coefficients and the friction factor. The friction factor is a scaled momentum flux. So, the scaled mass, momentum and energy fluxes are much higher than those for a laminar flow. Okay. For a laminar flow, just by dimensional analysis, if the density is not a factor determining the friction factor, then the friction factor necessarily has to be proportional to 1 over the Reynolds number, inversely proportional to the Reynolds number. Okay. And if you plot in a log-log graph the log of the friction factor versus the log of the Reynolds number, the line is a straight line with a slope of -1 for a laminar flow. For a turbulent flow, the friction factor depends not only on the Reynolds number, but also on the wall roughness, because when there is wall roughness, there are eddies created close to the wall because of the rough wall, and these result in additional dissipation as shown over here, and because of this there could be an additional increase in the friction factor if the wall is made rougher. And this was shown by the Moody graph here for a smooth wall and for rough walls. Okay. And these are also characterized by correlations such as the Colebrook correlation that I discussed at some length, which basically relates 1 over square root of f to the logarithm of square root of f of Re times square root of f, okay, as shown in this formula here. Okay. So, this is an implicit relationship, it cannot be solved explicitly for the friction factor. Okay. The left side it contains 1 over square root of f, the right side contains Re times square root of f plus something related to the wall roughness. I had simplified this Re square root of f for you and showed that this actually is independent of the flow velocity. Okay, it depends only on the pressure drop. Therefore, if the pressure drop is given, this is an explicit relation for the flow velocity. Okay. If the flow velocity is given, then you can directly calculate the pressure drop. It is an implicit relationship which has to be calculated by iteration. Okay. But correlations of this kind can be used to estimate what is the pressure gradient required to drive the flow at a specific velocity. Okay. So, the low Reynolds number or the laminar flow correlation is basically friction factor is proportional to 1 over Reynolds number. At high Reynolds number, it is an implicit correlation, or you have to get it from the Moody plot or from tables. Next, we will consider another prototypical flow, and that is the flow past okay. So, I have a flat plate here in which the area, okay, the cross sectional area perpendicular to the flow is infinitesimal compared to the length of the plate. Okay. Okay. The length is L and the thickness in the direction perpendicular to the flow is infinitesimal. So, it is not a parameter in the problem, and there is fluid that is incident on this, okay, with the velocity which I will call as free stream velocity. Okay. The relative velocity between the fluid and the plate at a distance far from the plate, okay, that is the free stream velocity. This is what is called a developing flow. Okay. The flow changes as you go downstream. The pipe flow that we had discussed earlier is a fully developed flow. Okay. That is, we assume that the velocity profile is independent of downstream distance, okay, at different downstream distances. Okay. That is valid so long as the length of the pipe is much larger than what is called the development length, okay, for the flow. For the flow to reach its fully developed parabolic profile for a laminar flow, or the turbulent profile for a turbulent flow. Okay. So long as the length is large compared to the development length, we can assume that the flow is fully developed in the case of a pipe flow, and therefore, there is no variation of the velocity profile with downstream distance, and the wall shear stress is a constant, okay, if the length of the pipe is much longer than the development length. Okay. The flow past a flat plate is not a fully developed flow. Okay. What happens is when the fluid is incident on the flat plate, right, the velocity was finite upstream of the flat plate, but at the surface itself the velocity has to be 0 because the plate velocity is 0. Okay. So, if you apply a no slip condition at the surface, the velocity at the surface of the plate has to decrease to 0, okay, and therefore, you had a constant velocity here upstream of the plate. At the surface itself, the velocity has to decrease to 0, and as you go further away from the plate, it will go to its free stream value. Okay. So, very far from the surface, the velocity has to decrease to 0. The velocity decreases to 0 because of the momentum exerted, because the force exerted by the flat plate on the fluid. The fluid is flowing with a certain velocity, the flat plate is stationary, and therefore, for the velocity to decrease to 0 at the surface, the fluid has to exert a force, I am sorry, the plate has to exert a force on the fluid, a stress to reduce the velocity to 0 at the surface. And since it is exerting a stress, there is a deceleration of the flow close to the surface, and that deceleration is within a region, okay, which is called the momentum boundary layer, okay, within a region called the momentum boundary layer, where the flow decelerates and decreases to 0 at the surface. The thickness of this region increases as we go, as the downstream distance increases. Okay. So, that is an important characteristic. Okay. Because the thickness of this region is increasing, if you go to some other downstream distance a little further away, okay, the velocity will decrease to 0 over a larger distance from the surface of the plate. Okay. So, in that sense, the velocity, the fluid velocity profile is developing as you go downstream. Okay. You can define a Reynolds number based upon the total length of the plate as rho V free stream L by mu, okay, based upon the total length. It is also necessary to define a Reynolds number based upon the downstream distance. Okay. If I use a coordinate x, okay, which gives you the downstream distance, at some location x, I can define the Reynolds number based upon the location x as rho v free stream x by mu. Okay. So, this is locally defined at each location within the flow. Okay. And this Reynolds number of course increases with downstream distance. Okay. Closer to the leading edge of the plate, the Reynolds number will be small. It will increase as you go further downstream. Okay. Now, this definition is important because there are two things that depend upon this. Okay. The Reynolds number based upon the downstream distance. Okay. If the flow past the plate, if the Reynolds number for the flow past the plate is sufficiently large, right, then the velocity profile at any downstream distance will not depend upon the total length of the plate. Okay. It will not in general depend upon the total length of the plate, because conditions downstream do not affect the velocity profile at a given location x. Okay. In other words, conditions at some downstream location do not affect the velocity profile at an upstream location, because flow is transporting momentum in the downstream direction. Okay. There is momentum diffusion across of course, which is in all directions, but if the Reynolds number is sufficiently large, the conditions at a downstream location will not affect the velocity profile at an upstream location. And therefore, as far as the velocity profile at some particular x is concerned, it is independent of the total length. Okay. It depends only upon the Reynolds number based upon the distance from the upstream edge of the plate. Okay. The boundary layer thickness is typically defined as the location. Okay. It is defined as the location, okay, where the fluid velocity in the x direction is equal to 99% of VFS. Okay. Okay. The height at which the fluid velocity is equal to 99% of the free stream velocity. The fluid velocity has almost become equal to the free stream velocity. Okay. That height is called as the boundary layer thickness delta 0.99. Okay. So, at this location, if the free stream velocity becomes equal to 99%, then this distance is delta 0.99. Okay. And this delta 0.99 depends upon the Reynolds number based upon the distance x. Okay. That thickness at which the velocity reaches 99% of the free stream velocity, beyond which the flow is virtually undisturbed by the presence of this plate. Okay. That is given by, this can be calculated. It is outside the scope of the present course, but it can be calculated if in our study of fluid mechanics. This is equal to 4.9 times root of mu x by rho times V free stream, okay, which is equal to 4.9 x times the Reynolds number based upon x bar minus 1 by 2. Okay. So, the thickness at which up to which there is a disturbance to the velocity field due to the presence of this plate, okay, beyond which the disturbance becomes less than 1%. Okay. That thickness varies as square root of x, okay, square root of the downstream distance from the leading edge of the plate, okay, for the flow in a flat plate. Okay. And this is applicable for a laminar flow. It is important. Okay. In the flow past a pipe, we had made a distinction between laminar and turbulent flows. That distinction also exists for the flow past a flat plate. In a laminar flow, the streamlines are smooth, steady, and there is no cross stream momentum transfer takes place only due to molecular diffusion. And once the transition to turbulence takes place, you have rapid cross stream fluctuations, large and motion of eddies within the flow, and cross stream transport due to fluid velocity fluctuations. Okay. the transition from a laminar to a turbulent flow in a pipe fully developed flow, it occurred at Reynolds number of about 2100. Okay. In a flat plate, the transition occurs at a particular downstream value, a particular value of the downstream distance from the leading edge, because this is a developing flow. Okay. It never reaches a fully developed state, okay, for the flow past a pipe, a flat plate. Okay. So, let me just shift this a little bit. Okay. At the downstream location where the Reynolds number based upon x is equal to 5 times 10 power 5. Okay. At this location there is a transition to turbulence. Okay. At this downstream location where the Reynolds number is equal to 5 times 10 power 5, there is a transition to turbulence. Okay. And within this turbulent region you have, okay, fluid velocity fluctuations in eddies, okay, in all directions, okay, which transport momentum. Okay. And in this region the boundary layer thickness increases as a different power. Okay. The distance at which you reach 99% of the free stream velocity, okay, that goes as mu x by x into Re x power minus 1 by 5th. Okay. This is for a turbulent flow. Okay, this is for a turbulent flow. Okay. And you can see that initially it is decreasing as Re power minus half, and after that it goes as Re power minus 1/5. Okay. So, these are the salient features of the flow past a flat plate. Okay. The velocity profile changes continuously with downstream distance. So, it is a developing flow. It may be steady, that is, the velocity at a given location does not change with time, but it does change as a function of downstream distance, and that is because as the fluid retards, as the flat plate exerts a force on the flow, momentum from the flat plate diffuses further and further, okay, into the fluid, and because of that the fluid slows down to a larger thickness in comparison to an upstream location. And this delta, the distance from the surface, the cross stream distance from the surface at which the velocity reaches 99% of its absolute value, it increases as Re power minus half for a laminar flow and Re power minus 1/5 for a turbulent flow. The transition takes place at a Reynolds number which is equal to 5 into 10 power 5. Okay. 500,000 is the Reynolds number based upon the free stream velocity and the free stream velocity and the downstream distance. Okay, that is the Reynolds number at which transition takes place. Now, if you recall, I had said that for a flow past a flat plate, okay, for momentum transport, the correlations are defined for what is called the skin friction coefficient. Okay, it is called the skin friction coefficient, which is basically the total force, drag force exerted by the, which is basically the average shear stress divided by half rho the kinetic energy per unit volume. Okay, that is the kinetic energy per unit volume in the free stream, okay, the free stream kinetic energy per unit volume, where the shear stress is equal to the total force exerted on the surface, the drag force that is exerted by the fluid on the surface divided by the tangential area, okay, L into W, okay, where W was the width of the plate perpendicular to the flow direction. Okay. If you recall, I had said that the width of the plate perpendicular to the flow direction is W. Okay. So, if you take the total force exerted on the plate, the force is of course a function of position on the plate, because the velocity profile is developing as it goes downstream. In that sense, it is different from a pipe flow. In a pipe flow, once the flow is fully developed, then the wall shear stress is independent of downstream location. In this case, because it is a developing flow, the wall shear stress does depend upon downstream location, and therefore, you define the average stress as the drag force divided by the tangential surface area, the surface area parallel to the flow direction. In this case, the force exerted is due to the tangential force exerted on the surface of the plate, because the plate has infinitesimal thickness. So, there is very little normal force that is exerted on the edge of the plate in comparison to the tangential force that is exerted on the surface area parallel to the streamlines. Okay. And you have different drag correlations, this skin friction coefficients, you have different correlations for the skin friction coefficients. Cf is equal to 1.328 by the Reynolds number power half for a laminar flow. Okay. And this is equal to 0.074 by Re power 1/5 for turbulent flow. What I mean by turbulent flow is that the length of the plate is much larger than the downstream distance at which the transition to turbulence takes place. Okay. That is, the length of the plate is much larger than the downstream distance at which the transition to turbulence takes place. In that case, the friction factor, the skin friction coefficient goes as Reynolds number to the minus 1/5, whereas if the length is much smaller, so that the flow is still laminar even at the downstream edge of the plate, in that case the skin friction coefficient goes as 1 over Reynolds number to the half power. Okay. And this is valid for Reynolds number less than about 10 power 7 or so. Okay. Okay, so, from about 5 into 10 power 5 to about 10 power 7. Okay. So, let us examine a concrete example to see what are the kinds of numbers that come out for the flow past a flat plate. Okay. So, let me consider the flow past a flat plate of air of density 1.25 kg per meter cubed is the approximate density of air at standard temperature and pressure, and viscosity, which is 1.8 into 10 power minus 5 kg per meter per second. Okay. Moving with a free stream velocity which is about 2 meters per second. Okay. This would be the free stream velocity for a gentle breeze, for example. Okay. Would be about 2 meters a second, 1 to 2 meters per second. Okay. And we can ask various questions for configurations such as this. Okay. Flowing past a flat plate, I said there is a laminar boundary layer, okay, and then at some point there is a transition to turbulence. We can ask the question, at what downstream distance does the transition to turbulence takes place? Okay. At what downstream distance does the transition to turbulence takes place? Okay. We know that the Reynolds number is rho VFS into the downstream distance x for the transition to turbulence divided by mu is equal to 5 into 10 power 5. Okay. I will call this as LT. Okay. Is the length at which the transition to turbulence takes place. okay, which will give us LT is equal to 5 into 10 power 5 into 1.8 into 10 power minus 5 kg per meter per second divided by 2 meters per second into 1.25 kg per meter cubed. Okay. Divide by the velocity and the density. Okay. And you can easily work this out. This comes to about 3.6 meters. Okay. So, for a gentle breeze of 2 meters per second, you need to go a distance 3.6 meters downstream for the transition to turbulence to take place. Okay. And this downstream distance is varies as the inverse of the velocity. So, if you double the velocity, the distance becomes 1/2, okay, and so on. Another pertinent question: what is the value of this boundary layer thickness at the downstream location where the transition takes place? Okay. And we know that delta 0.99 is equal to 4.9 into x into Rex power minus half. Okay. And in this particular case, the downstream distance is 3.6 meters, okay, and this is 5 into 10 power 5 is the Reynolds number per minus half. Okay. And you can do this calculation. You will find that this is approximately 2.5 into 10 power minus 2 meters. So, at a downstream distance 3.6 meters from the leading edge, the thickness of the boundary layer is only 2.5 centimeters. Okay. So, the disturbance due to the surface is restricted to a very thin region, approximately 2.5 centimeters from the surface. Beyond that, the flow is undisturbed, okay, by the presence of the surface. Okay. And this is typical. The boundary layer thickness is very often much smaller than the plate length, okay, by a factor of 2 orders of magnitude to 3 orders of magnitude. Okay. When the length is much smaller than the boundary layer thickness, than the transition length, then the skin friction coefficient is given by 1.328 by Re power half. Okay. The skin friction coefficient, you remember, was Ft by Lw whole divided by half rho L square, rho VAV L by mu whole power half. Okay. And if you multiply throughout by the kinetic energy per unit volume and this L times and the length of the plate, then you get the drag force is equal to 1.328, okay, into I have a 2 into rho V average square by 2 into mu by rho per half. Okay. This is Ft by Lw. Okay. So, you can easily see that this is therefore Ft, the force per unit width, okay, will be equal to 1.328 by 2 into rho per half V average per 3 by 2, okay, into mu per half, okay, into length per half. Okay. So, therefore, the drag force increases as the square root of the length. Okay. The drag force increases as the square root of the length for a laminar flow. Okay. The drag force increases as the square root of the length for the laminar flow. Okay. And you can calculate the numerical value for for these particular property values. Okay. On the other hand, if you have a turbulent flow, okay, if you have a turbulent flow, you know that Ft by Lw will be equal to half rho V average square, the kinetic energy per unit volume, into 0.074 by Re power 1 by 5 is equal to therefore, the drag force per unit width, okay, will be equal to 0.074 by 2 is 0.037, okay, into rho power 4 by 5, okay, V average power 9 by 5, and I have multiplied throughout by length here. So, I will get an L power 4 by 5 and mu power 1 by 5. Okay. And therefore, for a turbulent flow, the total force increases as the length to the 4/5 power, okay, in comparison to the half power for laminar flow. Okay. And you can calculate the numerical values of these. It comes to about approximately 10 power minus 2 newtons per meter for a laminar flow, and a similar number for turbulent flow times L power half and L power 4/5 respectively. Okay. So, the point I am making here is that to go from the skin friction coefficient to the actual drag force, you have to make sure that you take the correct powers of the length, okay, because the skin friction coefficient also has a power of length in it, okay, and the Reynolds number on the right side also has a power of length in it. Okay. Therefore, you have to take those two consistently in order to be able to calculate the drag force that you would have on a surface. Okay. And these kinds of things are important in in structures, like buildings and so on. When there is wind blowing across a structure, you want to know how much is the drag force on that, and these are ways to calculate it. First, calculate the Reynolds number based upon the total length, determine if it is laminar or turbulent, and then use the appropriate correlation to calculate the boundary layer thickness and the drag force. So, this is a summary of the flow past a flat plate. Okay. We have seen internal flow in a pipe, external flow past a flat plate. Next, we will see the flow past a spherical particle. I will continue this in the next lecture.